In this video, I want to show how to determine the voltage drop across an LED, and that way you can use Ohm's law to figure out what resistors you need for what given voltage you're applying the LED to. But before we do that, let's look at a little bit of math, and I'm actually going to use a slide rule. On the slide rule, we have a scale C and D. We're going to use the C scale for the resistor at 150 ohms. Now this says 15, but it's in between 1 and 2, so this is 1.5. So to make 1.5 equal 150, we move the decimal place 2 places to the right. That means that whatever we do on this lower scale, we need to move the decimal point 2 places to the left. The one on this end is going to be where our answer is, and wherever the 1.5 goes, so like there's 2 volts right there, so the 1 lands right here, and that's in between the 1 and the 2, so this is 1.3, but we need to move the decimal point 2 places, so this will be 13.3, so 13.3 milliamps. If I move it to 2.5, it's going to be 16.6. If I move it to 3, right here, then that means it's 20 milliamps, because 2 places to the left is 20 milliamps. And that's the maximum value any LED can take, is 20 milliamps. So that means that we cannot go past 3 volts on our test resistor. Over here are the leads for the power coming in, and this is going to be a variable voltage supply. And this is the 2 leads to my meter, and it's going to tell us what the voltage drop is across the 150 ohm resistor. The LED inside the optical coupler can operate up to 20 milliamps. Almost every LED can operate up to 20 milliamps. So that's our safety limit, is that cannot let this go past 3. So I turn up the external power supply. There's 1 volt, 2 volts, 3. And let's bring this up to, okay, that's close. Okay, so this means that 20 milliamps is running through this resistor, which means this LED, since it's in series, is getting 20 milliamps. And my power supply says 4.2 volts. So we also know that if we subtract the 4.2 volts by 3 volts, that this is 1.2 volts. So now we know that this LED inside here is rated at 1.2 at 20 milliamps. We can see that the power coming in goes to the emitter. I believe it's the emitter leg of a NPN transistor that's inside this, and then the collector, and then it goes through the LED. Now this is a 510 ohm resistor, so this is not operating anywhere near 20 milliamps. To prove that this is doing that, if I lift this leg right here, I turned off the LED inside of the optical coupler. I connect it back up again, and it operates. This circuit was not touched going this way. So this is actually functioning. So let's go ahead and just test this LED. So we put this LED in, and I turn up the power supply. We're just going to go up to 3 volts straight away. So this is like really, really bright. 20 milliamps is going through it. The power supply is reading 6.1. So this is 3.1 volts at 20 milliamps. Now I could take and look at this and say, you know, that's a good level right there. And since I have 0.3 and it's reading 2.6, then I could say that it's 2.3 at a different rating, also at a light level that I like. This LED is an infrared. You see inside there's a little ledge. That's the cathode side, and the anode's over here on the longer leg on this. So this is the plus side. Go ahead and plug that in and turn it up. And it's reading 4.2, so 1.2 volts is across this LED. And you can't see it because of the angle, and I can't see it because you can't see this kind of light. But if I point it towards the camera, you can see that you can see it. Now these, you can actually pulse them at a higher current and make them even brighter. This is an old Radio Shack infrared, and you can see that it says 100 milliamps at 1.2 volts. And I also have it rated at 20 milliamps at 1.6. So you can use this. If you use the higher current rating, you have to pulse it. You have to give it an on and off time so it can cool down so it doesn't burn up. So you pulse it on for a short duration of time and you cool down. It's probably longer on the cool down than it is on the turn on. And you could actually just check the heat and make sure that it doesn't get too hot, because if you're going to run it at the higher currents, then the heat's what's going to destroy it. And the same goes for a laser LED, and this one here says 200 milliamps, so definitely have to watch the heat on this one. The last LED looking device is this one. Now I know it has an LED in it, but it's got a little bit more than that in it. I know that the long leg is the plus side, so I'll go ahead and put that in there. And I'll go ahead and turn it on. And it's erratic, jumping all over the place. I know what it is. I pulled it from a one of those candles. So one of these you can't really determine. I wouldn't trust going 20 milliamps on it. Some things you can figure out. This you wouldn't be able to figure it out unless you knew it. So that's pretty much all I have to show for now. In future videos I'll be hooking up LEDs, and you should be able to connect LEDs up based on this video. One of the things that I've seen on the internet is that people will put in TTLs and just connect the LEDs straight to them and run a whole bank of LEDs off of a single TTL circuit. That's actually not designed to run that way, and it's not an appropriate way to do it, because you exceed all the current capability of the whole device. You can only have so much current going in there. If you have 8 LEDs at 20 milliamps, you're going way past the current limit on that whole device itself. So in my next video, we'll be talking about building a driver circuit for LEDs. So I hope you enjoyed this and got something out of it, and have a great day.